All right, I'm talking about 2.4, the chain rule today. The chain rule is another method to take derivatives. Really, the focus of this lesson today is just continuing with taking derivatives of all sorts of functions. Today we're going to start combining all the rules we've done so far, so product rule, quotient rule, power rule, which is always in play, and then and then also the 6 trig derivatives that we talked about in the last section. Okay, chain rule is used for when I want to take the derivative of a composite function. So a composite function, if you remember, is when I have one function plugged into another function. There's sort of a notational, there's a kind of a notational manipulation which I'll show you in class where this comes from. But for the most part, just remember if I take the derivative of a composite function, one plugged into another, I sort of blob out the inner and I take the derivative with that inner function intact, and then I chain out the derivative of the inner function. One of the more common errors is people will take all the derivatives at once, so they'll have like g prime here instead of the g that stays the same, and then chain out the derivative. So you want to chain out the derivative, thus chain rule, okay? So let's go ahead and take a look at this. Now, technically I could do this problem by multiplying this all out and then using power rule to the 7th power. That would be quite annoying. So we definitely want to leave it in this composite function. So we have the inner function, which is the 5x squared plus 2x, and then I have the outer function, which is to the 7th power. So the way this works is, okay, everything here remains intact. The 7 comes down, that drops to 6. Everything stays intact. Don't take the derivative all at once. That's a very common error. And then we multiply the derivative of what's inside. So this would be 10x plus 2. Now make sure this is in parentheses here. If you put this without parentheses, that would be incorrect. So that is our derivative. So once again, treat the outer function as it's just like the blob to the 7th power. The 7th power comes down, that drops to 6. Everything stays exactly the same inside, and then we take the derivative of that inner function. That is chain rule. Okay. Now this one, before we go, we want to rewrite this one. I could do a combination of chain and quotient, and we will end up doing that. For instance, here you can see we're going to do a combination of chain and product, but we can rewrite this so it's just a simple chain rule thing. So the way I'm going to rewrite this is I'm going to raise this to the numerator and use a negative exponent. So we still are going to use chain rule, but now we don't have to do that in conjunction with quotient rule, which makes it a little bit nicer. And once again, I want to stress, especially when we're doing the textbook problems, you don't need to simplify unless there's a compelling reason to do so. And we will see problems where we do want to simplify because we're trying to write the equation of a tangent line or something like that. Now, when you get to the delta math problems, those ones typically they're asking you to simplify those, so those you do have to simplify. Okay, so sort of blob this out, take the derivative of the outer thing, so that negative 2 drops down. Everything here stays intact. This drops to negative 3. 3x minus 5 stays exactly the same. And then we take the derivative of what's inside, which is 3. So you can go ahead and leave it like this. If I did have to simplify this one, it would be pretty easy. If I had to simplify it, I would call it negative 6 over 3x minus 5 to the 3rd power. But like I said, I'm not really all that interested in that for these, at least for the textbook problems. Okay, this one we're going to rewrite. So we have a fractional exponent. So this would be 2x squared minus 8. And we're going to raise that to the 4/5 power. Okay, so once again, we take the derivative of the outer function. So bring that 4/5 down. Everything stays intact, 2x squared minus 8. That drops to negative 1/5. And take the derivative of what's inside, that is 4x. And we're going to leave that as is for right now. And there you go. So far all the problems I've done, I've been able to rewrite them. So all I had to do was this chain rule here. In number 4, there's no way around it. I have a product here that I have to deal with. I've got to deal with these as 2 distinct factors. I am going to rewrite this term So this is going to be 5x and then 3x plus 1 to the 2/3 power. We're going to follow a product rule, and then when I take the derivative of this, I have to use chain rule. When we start combining these rules, people do get confused. They ask me which one you do first. It's not really the logic there. It's a product, so I got to take the derivative of this first, then copy that down, plus, and then when I take the derivative of this, I'm going to use chain rule, copy that down. The one thing I'll say is I'm going to throw a lot of these at you today, and then when you combine that with what we were doing in 2.2 and 2.3, it's going to take practice. It's going to take a lot of practice on your part, and you're going to see as we do these problems, I'm going to assign quite a few problems because it's going to take a while for you to get good at this. Okay, so let's take the derivative of 5x, that's going to be 5. Copy the 3x plus 1 down to the 2/3 power, okay, plus. Now we're going to switch it. Now we're going to take the derivative of this thing. So when I take the derivative of this thing, 2/3 comes down. That drops to negative 1/3. The gut stays intact, and then we take the derivative of that inner function, that's 3, and don't forget to copy down the 5x. So there you go. That is our derivative, and we are going to leave it ugly like that. Okay, I'm going to erase here to clear off this board, and then I'm going to continue doing examples. Mostly what I'm going to do today is just doing examples of different trig things. Or excuse me, different derivatives. Okay. Okay, so let's continue on with this derivative taking. 5 and 6 here, both are a combination of quotient and chain rule, but the way we're going to apply these are going to be different. Once again, we want to get away from this idea of, which comes first. It's not like order of operations where we always do multiplication before we do adding and subtracting. It doesn't work that way. Okay, so this is a quotient, so I'm going to use quotient rule. So when I take the derivative of this, I'm going to square the denominator. Now when I square the denominator, of course, that radical will just go away, right? So something squared, square root squared, the square root just goes away. Now we're going to take the derivative of the top first, so that's 2x, copy down the bottom. Okay, minus, now we're going to take the derivative of this. So when we take the derivative of this part, now we're going to use chain rule. Now if it helps, rewrite it like this, just so you can see it. So now when I take that derivative, the 1/2 comes down, x squared minus 3 to the negative 1/2. Now chain rule, we got to take the derivative of what's inside, that's 2x. Now don't forget to copy down the top, that's x squared. So, pretty involved here, but if you just sort of follow these steps, don't get thrown off by the fact you're combining different things. Now here, okay, we want to focus on the fact the outer thing is something squared. So I'm just going to bring down the 2 here. This drops to 1. Everything stays intact. Okay, and then we take the derivative of what's inside, which is going to be quotient rule. So we square the denominator. All right, take the derivative of the top, that's going to be 4. Copy down the denominator. Hopefully I don't run out of room here. It's going to be close. Okay, so copy down the denominator, minus, and then switch it. We're going to take the derivative of the denominator, and create a little bit more room here. All right, so let's take the derivative of the denominator here. So that's going to be 2x. Copy down the 4x minus 1. Hopefully you can see that. I kind of ran out of room. So we have 4, the quantity x squared minus 2, minus 2x, and then that is, let me put that up here in case you can't see it, 4x minus 1. You should be able to see the rest of it. Okay, so let me point out to you, both of these involve chain rule and quotient rule, but the sort of the order in which I applied them was different. Where here, the outer thing, if you will, was a quotient rule thing. So when I took the derivative of the bottom, I had to use chain rule. With this one, sort of the outer function, I didn't have to worry, I just did chain rule, but then the inner function was a quotient. Okay, okay, so we're going to go on to a few more derivative rules, and then we're going to continue with this process. So we just keep adding more and more to this. Don't freak out. I know that this is going to take some time on your part. Okay, so let me explain what we have going on here. We are going to take the derivative of these three functions. If I take the derivative ln of x, I get 1 over x. By the way, I want to remind you, we do already know the derivative of e to the x is e to the x. So the derivative ln x is 1 over x. X is greater than 0. You don't have to write that, but it's just something to remember because the domain of the original function is x is greater than 0. So our derivative isn't going to exist where our original function doesn't exist. So often when you see this, they'll qualify x is greater than 0. What I'll tell you is usually when you're using derivatives, you're going to want to pay attention to the domain in the first place, so you won't be analyzing that part of the function anyways. Okay, so the derivative of log base a of x is 1 over x ln of a. And let me point out to you that that does fit with this, because if I applied this rule generally to this, I get 1 over x, and that would be ln of e. ln of e would just be 1, okay? Same is true here, so that, oh, sorry, let's get this, I almost missed that. This is ln of a. The derivative of a to the x, so 2 to the x, 3 to the x, would be a to the x ln of a. So if you're taking the derivative of 2 to the x, it'll be 2 to the x ln of 2. E to the x, the derivative of e to the x is e to the x. So you can see that that does still apply, because that'd be e to the x ln of e. ln of e is 1. And that brings us to these properties over here. So this isn't calculus, these are properties we talk about. Now you'll see I did these mostly with just ln, natural log e to the x. That, 90% of the time that is what we're working with when we're talking about logs in this class. It's going to be ln of x, and the same is true with the exponential functions. Usually we do e to the x, not exclusively though, but quite often. These rules apply to any log of the same base. These can be very, very helpful, and if you just think about it in the context of derivative taking, if I have something that's in this form, I'd have to do like a chain mix with a product. But if I rewrite it like that, then I don't have to do chain or product in this particular case. So these come in handy. So you probably want to jot those down and have those nearby. So these are things you learned in, I think, Algebra 2. So ln of x times y is ln of x plus ln of y. ln of x over y is equal to ln of x minus ln of y. If we have an exponent, so like x to the c, we can bring that c down in front. Now, let's be careful, that's only if it's ln and the x to the c is inside. You can't do that if it's the whole thing being raised to a power. And then finally, these come in handy. We talked about this in the first chapter. Keep in mind, ln of x and e to the x are inverse functions of one another. So that means if I plug something into one and then into the inverse function, I get back with what I started with, which also can be very helpful because it's going to cut down sort of the amount of links in a chain rule type thing. So in this case, e to the x, if I do the ln, they undo each other and back to x. And the same would be true of a exponential base a and a log base a. And the same would be true here if I did e to the ln of x. So if I had, for instance, here 2 to the, and then log base 2 of x, they undo each other and back to the x. Okay, so let's take a look. We'll do these 2 examples and then I'll erase and we'll do a slew more. Okay, so right away, if I look at this, I could leave this as is and then do chain rule mixed with, just chain rule. But I don't have to, because what I can do is I can apply a combination of this rule right here and this rule here. So what I can do is I can rewrite this. So the way I would rewrite this is ln of 2, right, because that's a product, and then plus, and then this is going to be ln x to the third, and then keep in mind, x to the third, I can bring that 3 down in front. And what this sort of saves me is now I don't have to do any chain rule. So I'm going to take the derivative of this. Now let me point out to you, that's not going to be 1/2. The derivative of ln of 2 is 0. The reason why is ln of 2 is a constant. There's no variable here. One thing we have to grow accustomed to in this class is that constants don't always look the same. Ln of x is very different than ln of 2. ln of 2 is a constant. ln of x is a function, okay? So this will go to 0, and what we're left with here is the 3 in front for the constant multiple rule times 1 over x. Anytime we have a constant in front, we don't have to use product rule. It's just a constant multiple rule. Keep that constant out front. If you want to put this as 3 over x, you can do that. It really doesn't matter. Okay. Once again, number 2. I'm going to have to do a little bit with chain rule here, but I can bring down the 2, ln of x minus 3. So I want to point out this is log properties. I'm not doing any derivatives yet. Now, when I take the derivative, the 2 out front, constant multiple rule, derivative of ln of 1 over x will be 1 over x minus 3. And then I'm going to take the derivative of x minus 3, which is just 1, so that's not going to change anything. Okay? So let me erase, and we'll continue on with more problems. Okay, let's continue with a few more examples here. I'm going to be using all those rules we talked about, so we've got quite a few new tools in the tool belt. So we have chain rule now, we have the derivative ln of x, derivative log, derivative exponential, and then also we want to keep those log properties in mind because they can be very helpful to us. This is just a straight up product rule, no chain rule here. Derivative of x squared will be 2x, copy the ln of x down, plus, now switch it. X squared, derivative ln x is 1 over x. I could simplify that and make that x, but for right now, let's just leave it. Okay, number 4 I wanted to show you because some people will make the mistake of thinking I could use that log property to bring that 2 down before I take the derivative. I cannot do that. That's only if it's just the quantity inside raised to the second power. Since it's that whole thing raised to the second power, I do have to use chain rule. So let's blob that out. The 2 comes down. That drops to 1. Everything stays intact. Okay. Now, if there's problems that have multiple links in the chain, if you will, where it's a function inside of a function inside of a function, start outside and work your way in. Now we take the derivative of the ln of the blob, so that'll be 1 over the blob. Okay. And now we take the derivative of the blob, which is 1. Obviously, we don't have to write the 1, but just to show you how this would chain out. So we take the derivative of this outer thing, and then we move down to the next, and then we take the derivative of the innermost thing. Okay, this is just straight up log base 4, so that's going to be 1 over x, ln of 4. Sometimes people make the mistake of calling this ln of x. It's ln whatever that base is. The derivative a to the x, by the way, this just means the derivative of a to the x. There's no equation here. Would be a to the x ln of 8. Okay. This is a chain rule thing. Sometimes people get confused with e to the x. Oh, and I will tell you, make sure, I'm glad I remember this. People will make the common mistake of thinking that if I take the derivative of x squared, right, we take that 2 down, that drops to x, that's 1. That's power rule. If I take the derivative of 2 to the x, I'm not using power rule there. It all is about where the variable is. So if it's variable to a number, that's a very, very different function than 2 to the x. Okay? 2 to the x, we can't use power rule. You can't bring down the x, 2, and then x of minus 1. That is wrong every time. It's 2 to the x ln of 2. Okay, so make sure we keep those two things straight. For this x to a number, we use power rule. A number to x, we use the exponential rules. Okay, so we're going to blob this out here. The derivative of e to the x will be e to the x, or e to the blob in this case. And then we're going to take the derivative of the blob, which is 2x. Okay, I could also write that on that side. It typically looks a little better if you put that thing in front. Once again, this is chain rule, so we want to sort of blob that out there. By the way, the thing I say to blob is just basically like just sort of blob that thing out, just sort of treat it all as one term. So if I take the derivative of this will be the derivative of 2 to the blob, ln of 2. And then we take the derivative of the blob. The derivative of negative x is just negative 1. I'll just put that out front as a negative. If you do it with the parentheses negative 1 over there, that's fine as well. Okay. So that are some more examples, and I'm going to finish up with 4 more examples that deal with trig functions, and then that will be it for this video. Okay, we're going to do these 4 last derivatives, all that involve trig functions. Oh, I guess that one doesn't. And then that's going to be it. So let's start off with this one, cotangent, derivative of cotangent. The trig functions can throw people off. You just have to keep in mind that what logically works, there's a logic here that you should, through practice, you should get a hold of, but it is going to take a little bit of time. So the derivative cotangent of a blob will be negative cosecant squared the blob, and then we're going to take the derivative of the blob. like it was 6x plus 1. Make sure this is in parentheses because we have a binomial here, it's the whole thing. Okay, secant. People will be thrown off by secant and cosecant when it's chain rule. Realize that it's secant to the blob. Well, the derivative of secant x is secant x tangent x. So this is going to be, the derivative of this will be secant the blob, x to the third, tangent the blob, x to the third. And then take the derivative of the blob. I'm going to go ahead and write it out front just because it typically looks a little better. So that's going to be 3x squared, and there you go. There's our derivative. Okay, number 11, I want to point out that actually 11 and 12, both of these we can simplify before we go taking the derivative because we have log base 2, and then we're plugging in its inverse function 2 to the blob. So those are going to counteract each other, undo each other, and we're going to be left with y is equal to the square root of x plus 1. Let's call that x plus 1 to the 1/2. Okay, same is true over here. E to the x, ln of x, those are inverse functions, so they undo each other. So both of these are before we take the derivative. So we're left with y is equal to whatever went in there originally. In this case is tangent x. Now I can take the derivative easier. It's going to be much, much smoother. So y prime, 1/2 comes down, x plus 1 to the negative 1/2. Then we take the derivative of what's inside. Well, that's just 1. I don't need to multiply by 1. That doesn't change anything. And then over here, finally, derivative of tangent x is secant squared x. And there you go. Those are our derivatives. So once again, you know, I do realize that I did a whole lot of derivatives here, but that's what it's going to be about until we get this down. So that is 2.4, the chain rule. Happy derivative taking.